In this video, we'll be going over the solutions to lab problems from week 3. Now, this one is focused on inverses and transpose and doing some proofs with their definitions. So, first question here is asking us to find 2 by 2 matrices A, C, and D such that these specifications are met. So such that A does not equal 0, C does not equal D, but their AC equals AD. So I'll just quickly draw out what we're looking for here. So we're looking for A times some matrix C that equals AC, and the same A here multiplied by a matrix D giving us AD, such that AC equals AD, so these two are equal to each other, but C does not equal D. Okay, so we want A times two different matrices that will give us the same product. Okay, and an easy way to approach these type of problems is to set AC and AD to 0. So they're both the 0 matrix. And then from there, what we're going to do is we're going to essentially try and think of an A that will cancel out all of our values from our C and D matrices that will give us the 0 matrix. Okay, so we're going to set, like I said, set our AC, and I guess we can do our AD right now to 0, but right now we're just going to be focusing on this one right here. So if I set C to something like this, which is, it has all of the same entries here, then I just need to think about, essentially, I need to think of a way to get this row to be multiplied by this column here to give me this entry, to give me a 0. So I have to think about, okay, what can I multiply by 1, and then what can I multiply by 1 here, and what can I multiply by this one here, such that they will add together and give me 0. So like I said before, we're just going to be playing with positives and negatives with the A. So something that I could do is simply just doing a 1 and -1. So essentially, I'll be doing 1 times 1, and then -1 times 1, and that gives me, when I add them together, it's essentially 1 minus 1, so that's 0, right? And it works the same way for the second entry here, which will be this. And then same thing for the second row. I just need to somewhere have a -1 and somewhere have a +1. So I'll just do something like this. So I have, we'll take a different color here. So if I'm multiplying this one right here by my first entry here, and then the second one here by my second entry here, I'm going to end up with -1. So right here it will be -1 times 1 plus 1 times 1. So it's essentially 1 minus 1, which is 0. So I'm sure you guys get the whole multiplication part of that now. So same sort of idea for this one. We have the same A, 1, -1, -1, 1. And for D, we can choose D to be anything as long as it has the same entries. So I don't know, let's choose D to be 3. So in this one, same sort of thing. We'll have 1 multiplying right here by our 3. And so then this entry will be 3 plus, then we have this entry here multiplied by this. So that's plus -3, and that equals 0. So you guys get the idea. So essentially for these type of questions, an easy way to go about it is to simply try and play with the positive and negative signs to have everything cancel out, and you end up with the zero matrix. So you can see here that all of our conditions are satisfied. AC is equal to AD, check. A does not equal 0, check. And C does not equal D, so that's another check. So yeah, good way to approach these problems. And I mean, of course, you can also do it without it equaling to 0, but if you're on a test and you're kind of crunched for time, it's an easy way to go about it. Before we get into this question, we're going to quickly go over the fact that multiplication with matrices is not commutative. And what I mean by that, commutative just means that you can do something like if you have 2 times 4, it's equal to 4 times 2. So it just means that the order in this case does not matter, but that's not true for matrices. Okay, so this is not true for matrices. So for matrices, the order of multiplication really does matter. And I'll just give you a quick example here. So if we have something like 1, 1, 0, 1 times 2, 1, 3, 4. So let's call this one A and let's call this one B. Okay, if we write out the same thing here with B first though, and then A, so this should be a 1. So if we have B times A here, we see that this ends up being 5, 5, 3, 4, and this ends up being 2, 3, 3, 7. Okay, so this is the product AB and this is the product BA, and you can clearly see that AB does not equal BA. Okay, so I know that you're used to working with just numbers where it is commutative, which means that it doesn't matter which order that you're multiplying, but you have to really be careful for matrices that you don't make that mistake. You don't necessarily have that if you multiply 2 matrices together that that in the opposite order that it's going to equal the same product. Okay, so just something to be aware of before we tackle this question here. So we are given that AB equals AC, and we're given A inverse exists. We want to prove, so want to show, so this stands for want to show. We want to show that if this is true, then we have B equals C. Okay? So when we're approaching proof questions, one thing that we want to make sure that we do is, first of all, we understand what we have. We have these 2 things. So we're given these 2, and this is what we want to prove. Okay, so we have AB equals AC, and we know A inverse exists. So let's just write out what we have right now. So we have AB equals AC. Okay, so we want to eventually show, so somewhere down the line here, we want to show that B equals C. So we think about what do we need to do to this, what do we need to do to this in order to get B equaling to C? Okay, well, one thing that we have to do, well, actually the only thing that we have to do is to get rid of these A's somehow, right? If we get rid of the A's somehow, then we end up with B equals C. So that's when we go back to thinking about what are we given for doing this proof? What are we given in the question? And conveniently, we're given that A inverse exists. Now, we know from previous labs that A times A inverse just equals the identity matrix, right? And it doesn't matter, in this case, it doesn't matter which side the A and the A inverse are on, because it gives us the identity either way. So knowing this, what we're going to do is we're going to multiply by A inverse on the left side of this equation. And it's important that you're consistent with both sides here. It has to be on the left, because if you did something like, let's say you just wrote AB A inverse equals, I don't know, A C A inverse, something like this. In this case, because like we talked about before, we talked about up there, the order in which you multiply matrices does matter. So something like this, it won't necessarily give you so that you're able to cancel these two out. It doesn't work like that. Okay, if you want to cancel out the A and the A inverse, they must be right beside each other. They must be like this. Okay, so that's why it's important that you multiply. So multiply on the left by A inverse. Okay, because if you multiply on the left by A inverse, then you can see that you end up with A inverse times A here, which is perfect because A inverse times A, as we've talked about before, is just I, so the identity, times B equals I times C. So you guys can see what I did there. I just replaced the A inverse A with identity. And we know that the identity matrix times anything is just that thing. It doesn't do anything. It's the identity is like if we said 2 times 1, it would just equal 2, right? So it's essentially multiplying by 1. And then we can just leave it out and we end up with B equals C, which is what we wanted, right? So when approaching these questions, they can look sort of intimidating. So first thing you need to do is you need to, first step is, I'd say, write what you have. So that just means write all of the information that you have. In this case, we have that AB equals AC, and we have that A inverse exists, okay? So second step, I would say, is to figure out what you want to show. Okay, so in this case, we wanted to show here that B equals C. Okay, so you can write kind of like what you're starting with here, what you want to show, and what you want to end up with down here. And then you have to think about essentially how can I use what's been given to show what I want to prove. Okay, in our case, what we did is we said, okay, well, I'm given A inverse, and I do need to get rid of these A's somehow. So if I multiply A inverse by A, gives me the identity, which is essentially 1. And so I can just get rid of the A and A inverse together, and that gives me B equals C, which is exactly what I wanted. Okay? Okay guys, I don't know if you guys want me to go over another example of this, because it's essentially the same thing that we did in our first question. So was it the first question? I think so, yeah. So it was, we have to give an example of matrices such that neither A nor B equals 0, and yet their product equals 0. So it's the same thing, the same example from the first one applies. If we did, I don't know, 1 and -1, -1 and 1, and we call this A, and we multiply it by 2, 2, 2, 2, B, then that gives us a 0 matrix. So AB equaling 0. Okay, but neither A is 0 nor B is 0, but AB equals 0. So this one is essentially asking us to find like non-trivial solutions to AX equals 0. Okay, so non-trivial meaning where, you know, A nor B equals 0. It basically same sort of thing that we did in the first question is we want to figure out, we just want to play with these positive and negative signs and figure out a B where we can just cancel the values out to give us 0. Okay, so I think you guys are pretty good with that. All right, so this question is asking us to find the solution to the systems using inverses. So the solution to the systems meaning that we still want to find this x, y, and z values such that it makes the system true. So we're trying to find these that I'm highlighting right here. Okay, we want to find our x, y, and z values. So first of all, we have to do it using the inverse of the matrix. So you notice these matrices here are all the same. So we just need to find the inverse of this matrix A, we'll call it. So we have 1, 0, 3, 2, 3, 4, 1, 0, 2. So I'll just quickly talk about how to find the inverse of a matrix. So if you have a matrix, like you have your A right here, just a regular A, what you're going to do to find the inverse is you're going to set it up like I have here. So you're going to have the identity matrix beside it, just like in an augmented matrix. Okay, so essentially what it is you're going to start with your A matrix here and your identity on this side. Okay, when you're going to do reduced row echelon form on A, so you're going to do row operations until you get something that looks like this. And what I mean by this is that you're starting with your A, and then what you're going to do is you're doing row operations. Okay, you're doing row operations just like normal, and then you're changing A into the identity. So you're changing it into reduced row echelon form. Okay, just like you've always done before when you're solving systems, except for this time, what you're going to end up with is you're going to end up with your A inverse on the right side of this augmented matrix line. Okay, so I'll go through it and it will make sense. So we start with this guy right here. So this is our starting point. So first thing that we're going to do is we're just going to do normal row reduction. So in this case, what I did is row 2 minus 2 row 1, and I also did in the same step row 3 minus row 1. When you get to elementary matrices, which is the next topic, I think, you're not going to want to combine steps like this, but in this case we're not too worried about that, so I'm combining steps to save time. Okay, so you see that in this one I do regular, I'm just doing row 2 minus 2 row 1, so you can see that right here, and whatever I do to this side I'm also doing to this side, just same thing as if I had, you know, if I had just one column in there. Okay, nothing changes. Doing row operations on both of the sides. Okay, my next row operation, I will do row 1 plus 3 row 3 and row 2 minus 2 row 1. So I end up with 1, 0, 0, 0, 3, 0, 0, 0, 1. Okay, and then I carry that over onto this side also. Okay, and I do the same sort of thing. So I'm going to go row 2 times 1 over 3 and row 3 times negative 1. And I will end up with just the identity on this side, so reduced row echelon. And on this side, I'll end up with this. Oh, sorry, not this. I need to divide by 3 and multiply by negative 1. Okay, so this right here, this is my A inverse and my I. So you see from above how I said here that I'm going to end up with my identity on the left side now and my A inverse is going to be on the right side. Okay, so that's what happened here. So this right here is my A inverse, and this is what we're going to use for the calculation of our solutions to our system. Okay, so by now you guys should have seen this formula, AX equals B. This formula just means this is essentially the formula for solving a system of equations. So right here you've got your matrix A, and here you've got your solutions, and this is what it equals. So we'll call it like what solutions equal, or what system equals. And what I mean by that is I don't want to confuse anybody, so I just am going to write something like, let's say 2x plus 3y equals 4, and let's say negative x plus 4y equals 7. Okay, so essentially your A is going to be these numbers. Okay, so that's your A. Your X is going to be your solutions, so whatever your variables end up equaling, that will make this whole statement here true. So your X is your variables, are your variables, and your B is going to be what the system equals. That's what we're calling it, what the system equals. Okay, so that will be your B. Okay, so that's just a way of writing what we've been doing all along, AX equals B. And now what we have to do is we are trying to find X, right? And we have A inverse. We know that A inverse exists, right? So if we think back to our previous questions, it's kind of the same sort of idea with a proof. So what we want, or what we have right now, is this. We also have A inverse because we just calculated it. And what do we want? Well, we want X equals something so that we can calculate X, right? We want to solve the system. So if we want X to equal something and we know that we have A inverse, then something that we could do is we could multiply on the left. So once again, order of multiplication matters. So we're multiplying on the left by A inverse. And what does that do for us? Well, it essentially cancels that out because it becomes the identity, because A times A inverse becomes the identity. So we're left with something that looks like X, which is exactly what we wanted, equals A inverse B. Okay, so hopefully you guys get why I multiplied on the left by A inverse, because we wanted to get X equals something, and the only thing that's standing in our way from getting X equaling something is this A here. We need to get rid of the A, so we multiply it by our A inverse. Okay, so we end up with this formula here. So X equals A inverse B. And what we're going to do is use that to calculate all of our solutions to our system here. Okay, so I'm just going to erase this stuff here. I'm going to erase it so that we can do our actual calculations here. Okay, so as I said before, we're trying to find our x's, so we're trying to find our x using this formula that we found. So we're going to use this formula here to guide us through all of our calculations. So A inverse, we have A inverse is, so let's just start, let's number them so that we don't get lost here. We'll do number 1 is this one, 1, 2, 3, and number 2 is this one, and we'll do number 3 is this one. Did I say 3 or 2? Anyways, and number 4 is this one. Okay, so we have this formula here, x equals A inverse B. Okay, we're just going to use this formula to figure out our first one right here. Okay, so this is our A, this is our x, and this is our B. So we have two of the needed values here. We have our A inverse, which we calculated before, which is -2, 0, 3, 0, 1 over 3, and -2 over 3, 1, 0, -1. So this is our A inverse. And our B in this case is right here, 1, 2, 3. Okay, so we're just doing matrix multiplication here. So we're just multiplying right here, this by this. And if we multiply -2 times 1 plus 0, so -2 times 1 plus 0 times 2 plus 3 times 3, well, that gives us 7. Okay, and then same sort of thing here. We're multiplying this row here by the column, so we have 0 times 1 plus 1 over 3 times 2 plus -2 over 3 times 3, and that gives us -4 over 3. And same thing for our last row here, multiplying this row by this column, and that gives us -2. Okay, so this is our x value. This is what we wanted to find. So we found it. Perfect. Okay, so our next one is, we're doing the same thing, so multiplying A inverse times our B. So our B in this case is 1, 0, 1. So we have A inverse B. B equals our x. And in this case, it ends up being 1, -2 over 3, and 0. So right here is our answer, our solution. Okay, and same thing. I'm just going to write A inverse here, but it's the exact same one as this one right here. The same values, I just don't want to write it again. So next one is 2, 1, 0. This is our B. And it equals 4, 1 over 3, and 2. So this is our x for this. This is our solution to our system here. And last one, I'm going to just write A inverse again. We have 3, -1, -2. And that equals this is our x. So I hope that's okay with you guys, that I'm not going through the actual multiplication of it. Well, I did on the first one, but if you guys do need help with this, then you can go and look back in the video, the last video. We covered matrix multiplication in there, but I think you guys should mostly be okay. It's just practicing. It's kind of weird at first, but you'll get used to it. So here's the solution here, or I guess the solutions, I should say. So we have this one corresponding to this one corresponding to this one. This one is the answer for here, and this one's our answer for our fourth one. Okay, so all we did is we found our inverse. So for these questions, if you have to find the solution of the system with the inverses, so your first step is find the inverse, so find A inverse. Your second step is to recall the formula, first of all, for the solution of a system, which is AX equals B. Okay. Your third step is isolate for X using the fact that we found A inverse, so that A inverse does exist. And 4, use formula X equals A inverse B to find your solution here, X. So you're just doing matrix multiplication from that point on. Okay, I hope that makes sense. So this question is really just kind of an extension of the last question. It has the same A here. A is the same, and we just have a different B value. So the B value in this case is just in terms of other variables, so A, B, and C. So same sort of thing. They're not exact numbers, but you're using the same idea here. So we have A inverse from our last question. We calculated it, and because it's the same A, it's going to be the same A inverse. Okay, so this is our A inverse, and we're using the formula, sorry, not A, X equals A inverse B that we just talked about in the last question. So we're doing the same sort of thing here. We're multiplying A inverse times our B, not B, and it's giving us our X. So our solution to our system, which in this case is a minus 2A plus 3C, 1 over 3B minus 2 over 3C, and A minus C. Okay, so just because there are letters in here, don't let it confuse you. It's the same thing. This could be like a 2, and this could be a 3, and this could be a 1. It's the exact same thing as we were doing before, just now with more variables. Okay, so this is our solution. This is our X in this case. Okay, this question looks a little bit intimidating and a little bit scary, but I promise you guys that it's not too bad, and you'll be able to understand it by the end of this. Okay, so what this question is asking is, it's asking, so if A is an invertible matrix, so A is some matrix, then so is A transpose. So it's just telling us this right off the bat. And this property holds. So what does this property mean? Okay, so this one is saying that the inverse of A transpose, so the inverse of A transpose is equal to A inverse transposed. Okay, so what does this even mean? So this just means that, so for example, let's say I gave you the number 2, okay? And I said, so the inverse of 2 is equal to 1/2. So I said like the inverse of 2, so that's how you say inverse of 2 is 1/2, right? And you guys can agree with that. So now this is all that this is saying here, just it looks like confusing notation. So I'm saying, so the inverse of 2 is equal to 1/2. Now, how could you show me that that's true? How would you show me that the inverse of 2 is 1/2? Well, one way that you could do that is you could say, well, I'm going to show you that 2 times 1/2 equals 1, right? That's the definition of an inverse. So definition of an inverse, you multiply it by something and it gives you back the identity. In this case, our identity is 1, right? So this would in fact show me that, yeah, this is the inverse of 2, but I would have to do it both ways. So 2 times 1/2 equals 1, and 1/2 times 2 equals 1. And that's right. That's true, right? So if you guys can just kind of try and see past this terminology, or I mean this notation here, then it's really not too bad of a concept. So all we're going to do is the exact same thing, except for we're going to do that with A transpose, okay? So we need to check 2 things, okay? So we need to check 2 things. Okay, so recall that we're trying to figure out if the inverse of A transpose, so I guess I should erase some of this because it's a little bit clouding up what we're supposed to do. So we're trying to figure out if the inverse of A transpose is equal to this thing here. Okay, so like we said, our A transpose in this case is like our 2, and this thing here is like our 1/2. So what we're going to do is we're going to check if A transpose times this thing here, A inverse transpose, gives us the identity. Is that true? Does it give us the identity? And the second thing, because we have to test both sides, we have to test both ways, I mean, of multiplication, and this is just because, like we talked about earlier, matrix multiplication is not commutative, so we do have to check both sides. And I mean, we have to check both sides of an inverse anyway, so we're going to check if this thing here, this supposed inverse, multiplied by A transpose equals I. So those are 2 things that we need to verify. Okay, so one rule, so an important rule to note before we begin doing this is that if we have something like B, or let's say B transpose multiplied by C transpose, so 2 matrices, both of the transpose, we have that, it's equal to CB transpose. So in other words, you can put them both into like the same bracket here and transpose both of them on the outside. But something to note though is that the order of the matrices here changed. Okay, so if you have B transpose times C transpose, then if you put them together in a bracket, then it becomes C times B. Okay, so the order of the matrices changes, but you can transpose them both. Okay, so that's something important to note before we begin to verify this. So let's start with our number 1 here. So we have A transpose times A inverse transpose equals, Well, because we just talked about this rule here, we notice that, oh look, we have a transpose times a transpose. Doesn't matter what's in here, you can ignore this thing, it might intimidate you. But we notice that we have a transpose times a transpose. So we know that we can put them together and transpose both of them together. So we end up with A inverse A transpose. And of course, remember that, like we said before, the order switches here. Okay, so just like this BC example, we have A times A inverse, so we know we have to switch the order. Okay, so we have A inverse times A transpose, but as we've talked about many times before, A inverse times A, well, that just equals the identity, doesn't it? So we have identity transposed, and that just equals the identity. So we can just check this off and say, yep, that works. So it works for the first case here. Let's see if it works for the second case. So similar type of setup here. We're just writing what we have. And once again, we notice we have a transpose times a transpose. So some matrix transpose times some other matrix transpose. So we know that we can collect the terms in here, and we'll get A inverse transpose. And once again, this just is equal to identity transpose because A times A inverse is the identity, and this just equals I. So we can check this one off too and say, yeah, it works for both cases. So just like right here, we ended up getting our identity. Oops, I don't know what I did there. So we end up getting our identity here and our identity here. So we can verify that, yeah, in fact, it is the inverse of A transpose. So we would write something like, thus, we'd say A inverse transpose. So this thing that we were supposed to prove that is the inverse of A transpose. So A transpose inverse equals A inverse transpose. Okay, so this right here is just means the inverse of A transpose. Okay, so that's our solution here. So approaching these problems, you just really have to break down like what these notations are saying here, and from there you can kind of well, in this case we had to use these two cases here. We needed to prove that it equals the identity, because if you have, you know, something times something else equaling the identity in both ways that you write it, so in both order that you write it, then they are inverses of each other. So we just used the definition of inverse, and then of course we used this important transpose rule here. So before we start on the solution to this problem, I'm just going to make note of something, that matrix multiplication is associative. And what associative means is that you can re-bracket things and it's still going to equal the same thing. So associativity is talking about bracketing. Okay, so I'll give you an example here. If you have like 2 plus 3 plus 1, it's equal to 2, plus 3 plus 1. So something like this. You guys know this to be true. So if you re-bracket something, it's still going to be the same thing. This is also true for matrix multiplication. So if we had like A times B times C, it's equal to A times BC. Okay, so we can re-bracket things and it's going to be the same. It's going to equal the same thing. Okay, so that's important for this question. So this question is essentially same sort of idea as last question. We have this matrix AB, and we want to prove that the inverse of it is equal to this thing. Okay, so we want to prove essentially that if we have this and we multiply it by this, and vice versa, if we have this and multiply it by this, that we get the identity back. So that's just what it's saying right here. Just like we did in the last problem, we want to find out if, in fact, the inverse of AB is equal to this thing here. Okay, so then we have our two cases. So they give us the cases, which is very nice. So we have AB, our first case, times B inverse A inverse. Okay, so what we want to do is we want to somehow get this to be the identity. So let's just take a look, and keeping in mind what we just talked about here so that we can re-bracket stuff to get what we want, we notice that we have a B and we have a B inverse that are right beside each other. The only thing holding us back is these brackets here. So what we're going to do is we're going to re-bracket it, because we're allowed to do that. So we're going to re-bracket it so that these B's are right beside each other. And because they're right beside each other now, this suddenly becomes the identity, right? Because B times B inverse, or something times its inverse, it gives us the identity. So now we have A times I times A inverse. But you know that anything times I is just itself, so we can leave the I out, and we get A times A inverse. So we can put this in brackets here if you want. And as we know, just like we talked about, A times A inverse, this equals the identity. So in fact, we've proved it for this side, this way. Okay, so that way works. Now we're going to check the other way just to make sure. So we have, in this case, we have B inverse, A inverse, multiplied by AB. So same thing that we're gonna utilize is the rebracketing principle here. So our associativity. So we have A inverse times A, right? We see that. All we need to do, once again, is move these brackets here. So we're gonna do that. We're gonna go B inverse times A inverse A times B. Now you see right here, we have A inverse times A, which we can think of, that gives us the identity. So we have B inverse times I times B, and we'll rewrite that because anything times the identity is just itself. And then we're left with B inverse times B, which is just the identity. So in fact, that works too. Okay, so in this case, we've proved exactly what we're supposed to prove. So just multiplying these two together, it proves that if we end up with the identity, then they are inverses of each other. So you guys, this question is pretty much the exact same as the last one, except for now we have 3 terms in here. Okay, so we're trying to show that, so the inverse of ABC is equal to this guy here. And how do we show that the inverse of something is something else? Well, we multiply that something else by that something. Okay, that was a lot of somethings, but you get what I'm saying. So we're multiplying. So if we, once again, if we had, 2, and we said, okay, well, the inverse of 2 is actually 1/2. Well, we could just multiply those two together to get the identity, and that would prove to us that, in fact, yeah, this is the inverse of 2. Okay, so that's the same thing that we did in the last questions, just a reminder. So this one, we have now we have A, B, C, so we have 3 variables, and same sort of thing holds, associativity. So we are allowed, we are allowed to rebracket. Okay? We are not allowed to change the order of these things at all, so we can't just, you know, move the b over here. We can't do that. Okay, but we can rebracket. In this case, it works out for us. Okay, so don't try and move things around. You can rebracket though. So in this case, we'll have AB, and we have C times C inverse, B inverse, A inverse. Okay, then we end up with C times C inverse is just the identity. So we can just write it like this. And then we have B and B inverse in the same brackets. So we just end up again with the identity, which just equals this. And A inverse times A, as we know, it just equals the identity. So we end up with this equaling identity, this equaling the identity, and this equals the identity. So in fact, in this case, this is true. Okay, now we have to check the opposite way. So now we have to put the supposed inverse on the left. Okay, so same sort of steps here. We're going to rebracket it so that we have something that looks like what we want it to look like. So here we have an A inverse and an A together. So you can see we just rebracketed it so it looks more like what we want it to look like. So we have C inverse, B inverse, then we have the identity, and of course the identity matrix multiplied by anything. The identity matrix multiplied by anything is just itself, so we can leave that out. And in this case, again, we have B and B inverse equaling the identity. And the identity times anything is itself. And so C times C inverse, we end up with the identity again. So yes, this works. So in this case, we have verified that these two things are true. And so we can say, therefore, the inverse of ABC is in fact C inverse, B inverse, A inverse. Okay, so that's our answer here. So the last three questions were very similar, but it's a good thing to practice these type of proofs to make sure that you get the whole concept of inverses.